Alrighty, this video is going to go through the two-star questions of chapter 17. So let's begin with that. The first one here is number 20, and it reads, a 1 centimeter height object is placed 10 centimeters in front of a concave mirror of 7 centimeters focal length. Draw a ray diagram to find the position of the image, describe the nature, use the mirror formula to find the exact position, and use the magnification formula to find the height of the image. So A and C, they're kind of doing the same thing. One is using the one technique to find it, and then C is going to use the other technique to get a more precise version of it. I always like to do this even if I've just been asked to do a ray diagram, just because I want to make sure I'm getting that my technique is correct. It's a good way to check your technique. So firstly, let's go through and list off what we have here, because we're going to need to do some calculations. So we've got a 1 centimeter height object, so height naught equals 1 centimeter, and it's 10 centimeters in front. So excuse me, distance to the object is 10 centimeters, and we're told it is a concave mirror, so that means we're going to have a positive focal length, and it is 7 centimeters. So F equals 7 centimeters. Okay, now drawing our ray diagram, I'm going to show you a simpler version of the ray diagram today. So we still have our principal axis, we need that. We're dealing with a concave mirror, so we don't need much off to the right, and this time all I'm going to do is just put a straight line for my mirror. Now, how straight is that? That's not very straight. I know that mirrors aren't straight, but the curvature should be pretty small. Okay, and if it is small enough, then you don't need to really worry about how much of a curve there actually is. It'll still be inaccurate a little bit, we've seen that before, but it does save a bit of hassle. Only worry about using compasses if you're really trying to be precise. So let's go through. We need that the distance to the object is 10 centimeters and that the focal length is 7. So let's mark that off. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So this is where the focal point is, and this is where our DO is. This would be a good one to use, just a 1-for-1 scale, so 1 centimeter on your ruler, and we are 1 centimeter tall, so about yay high. Okay, so let's draw our two lines. Primary line, remember, is from the head of the object to it's just being difficult. Let's do that one again. Remember, from the head of the object to our mirror seem to want to be locking into a grid. It's very annoying. Let's do it freehand. This was going to really suck, but from here and then back through the focal point, and the second one goes through the focal point to the mirror. It's going to be somewhere down there, and then back roughly on a straight line. Okay, so this we need to go way further back. Alright, so we would have something like this. We obviously need to count back a bit, so it's going to be about 11, about 12. So I would say DI is roughly 13 centimeters. Now the question for this first part just wants to find the position. It's not asking us to find the height, it's not asking us to find anything else from this, just about the position. So I'd say it's roughly going to be about 13 centimeters there. Now the second part of the question is asking us to find what is the nature of it. So Here's A, and obviously that's pretty poor. I would recommend really doing that with a ruler, but my straight lines are not doing very well. Okay, so describe the nature. Firstly, real or virtual? It's in front of the focal point, must be real. Secondly, upright or inverted? We can see it's on the bottom half of the principal axis, so it is inverted or upside down. Smaller or bigger, we can quite clearly see it is enlarged there or magnified. And double checking our answers in the textbook. Yep, those are the three answers they're giving us. Oh, checking the answer in the textbook. I'm definitely going to be off on my drawing here. So C, now we're going to calculate. So 1 over F equals 1 over DO plus 1 over DI. Okay. 1 over 7 equals 1 over 10 plus 1 over DI. So 1 over DI will equal 1 over 7, take away 1 over 10. 1 over 7, take away 1 over 10, gives me 3 over 70. So DI equals 70 over 3 equals 23.3 centimetres. And as these have been two decimals, round this to two figures as well. So 23 centimetres. Had the 3 right at least, but yeah, obviously my drawing is pretty bad. Okay, D, use the magnification to find the height of the object. Sorry, the height of the image. So we know that M equals negative DI over DO equals height of the image over height of the object. So we're going to use this half of the equation. We don't need to go, we could solve it to M and then go back, but we don't need that. So that means we're going to have negative 23 over 10 equals height image over 1. That was 1 centimetre, wasn't it? Yes. So then height of the image, well, 1 doesn't matter, so it's just going to equal negative 2.3 centimetres, and negative would mean it's upside down, which we can see. 2.3 is bigger, which we can see, and so we know that, okay, well, at least that part of my drawing was okay. Alright, let's move on. 21. A dentist wishes to use a concave mirror to view a patient's teeth. If he wants the image to be twice as large as the object and upright when the mirror is placed 2 centimeters from the teeth, what focal length mirror is needed? Okay, so we have a magnification. We want it to be upright, which means our magnification must end up being positive. And we're going to, after we figure out that, so we're going to have the DI. After that, we can then work backwards to find out the focal length. So let's list down what we have here. We know that M equals 2. Okay, and hence we know that DO equals 2 as well. Okay, so first step is we need to work out what is DI equal to. And remember that for a concave mirror, so looking like this, if this is the focal point, if we're in here somewhere, then our image will be behind it. Magnification, we might have to bring it really close, so that'll be part of what we're going to have to figure out here, but from what I can remember from our 1-star question, we're going to have to be pretty close to the focal point, but it should be possible, so let's see how we go. Okay, so 2 equals negative DI over DO. That means that, well, sorry, let's substitute that. 2. Then DI will just equal negative 1. Now let's use our focal point. 1 over F equals 1 over DO plus 1 over DI. 1 over F equals 1 over 2 plus 1 over negative 1. So we're going to have 1 over F, well, half plus 1 is going to be 1.5. So F equals 1 over 1.5. Sorry, no, it won't equal 1.5. That was a silly mistake. That would be plus negative 1, so that would be take away 1. So half take away 1 equals negative 0.5. 1 over negative 0.5 equals negative 2. So if we double check our math looks right. If we double check in the answer here, we see that, well, they haven't given us an answer here from the look of it. At least they have 21.4 centimeters. So that tells me I've done something wrong here. So let's go back and double check, because we've done something wrong. Okay, so we're told it's concave mirror, and we want the image to be twice as large as the object, so m has to equal 2. We want the image to be upright, so m has to be positive 2, and the DO must be equal to 2 centimeters as well. What focal length is needed? Well, I can't see what mistake we could have made here. Now, these textbooks are not always 100% accurate, so I am going to just quickly check. No, nothing listed on the website for errors. Alright, now we've been given an answer of f equals 4. We're doing question 21, aren't we? Yes. So f equals 4 centimeters. So let's maybe work backwards from that and see what we get as a DI, and see what our, perhaps what maybe assumption we might have made wrong here with this. Okay, so this is a technique that's useful for studying in case that you find something that you're not really quite sure on how it got to. We'll start with the answer and work backwards. So if we have f equals 4, then we would have 1 over 4 equals 1 over 2 plus 1 over di, which means that we would have 1 over di equals 1 over 4, take away 1 over 2. Well, that equals negative 0.5. No, it doesn't. 1 over 4, take away 1 over 2. So it equals negative 1/4. Okay, so then di would equal negative 4. Okay, so I must have done something wrong here with, oh, I know what I did wrong. Before, when I had m equals negative di over do, and then I substituted it, so I had 2 equals negative di over 2, I divided when I should have multiplied. So, simple algebraic mistake. Again, on a question like this where I arrived at a nonsensical answer because I knew I should have had a positive f, that would have given me, let's see, negative 4. Alright, and now we can see that, yep, that follows back to the correct answer. On an exam, in a case like that where you've made an algebraic mistake and then followed it through, if you'd left it as that, you could still get a bit of part marks because you're doing the correct method, you've just made a simple mistake that's caused a problem. But the fact of the matter is that I arrived at an answer that really couldn't be right at all. F can't be a negative number, it's a concave mirror, F has to be positive, which means that you should have picked, well, in that sort of case, if you repeated my mistake, it would be expected you'd pick it up and go, oh, no, there's something wrong there. Even if you just identified this is wrong, and then gone on and done other questions, if you had time at the end to come back to it, great. But maybe you couldn't have. If you'd identified that it was wrong, that would still be worth more than if you'd just gone, oh yeah, f equals negative 2, or negative 4, whatever, I think I got negative 2, and then just left it at that. Okay, getting f equals negative 2, and then saying, no, that's wrong, that can't be right, that would be good. sort of mathematics and physics, okay? Because it's saying that you can interpret and understand your answer. If you don't come back to it, you still, like if this was a B standard question, you wouldn't get a B for it, but you'd definitely get a B minus for saying, no, I've recognised this is wrong, but I don't have the time to fix it yet. I'll hopefully come back to it at the end. Okay. Also, important to see that I am not infallible and I do make mistakes sometimes. Okay, question 22. Students doing experiments with convex mirrors, so negative focal points, the length place a small candle 15 centimeters in front of the mirror. They are able to see a smaller image of the candle in the mirror, but are unable to produce an image on the screen. Explain why an image cannot be formed on the screen. Use a ray diagram. Alright, so let's think about this for a second. We have our candle. It's in front of a convex mirror. Right? So thinking about our ray diagrams, it means our focal point is somewhere here, 2, and then backscatter towards them, and then away, which means we backscatter and we see the candle would be, well, it's a terrible candle. Something like that. Okay, I can't draw candles either. So we would see a smaller image, okay, but because this is it's behind the mirror, this is a virtual image. Okay, so therefore it can't be projected on the screen. The image is not being created in front of the mirror, it's being created behind the mirror. Therefore, can't project it. Okay, and the ray diagram here is showing us that. What sort of images? I would just said that as well. So virtual, so B. We could also discuss the other aspects of it. So we could say it's upright, and we can also say it's reduced or smaller. Okay, and finally, C. If the focal length of the mirror is 20 centimeters, calculate the position of the image. All right, so this one's pretty straightforward now. F equals -20. DO equals 15. So we need to find DI. 1 over -20, take away 1 over 15 equals 1 over DI. So -20, take away 1 over 15, gives me -70, -7 over 60. So DI equals about 8.6 centimeters, -8.6 centimeters, or 8.6 centimeters behind the screen. Okay, let's move on. 24 is next on the 2-star list. A student places a 5 centimeter high candle 20 centimeters in front of a concave mirror. The image is formed on a screen placed 40 centimeters from the mirror. What is the focal length? What is the size of the image? Is it virtual or real? Is it upright or inverted? Okay. Firstly, we can answer C straight away. We're being told it's projected onto a screen, so that means it has to be real. Let's go through the rest of it though. So we've been told it is a 5 centimeter height candle. Height object equals 5. We are told it is 20 centimeters in front. Distance object equals 20. And we're told that the image is 40 centimeters away. Distance image equals 40. So 1 over F equals 1 over 20 plus 1 over 40 equals, well, that would be 3 over 40. So F equals around 13.3 centimeters. Okay, next step, where is it? 24. What is the size of the image? Okay, so we need to know how big is our image, what is height image. And we get that through using these numbers. We could create magnification, but we'll we may as well actually, because it's going to help answer part D, so let's do it that way. So B, M equals negative DI over DO equals -40 over 20 equals -2. Okay, so this number will be useful. And m equals height image over height object. So height image will equal -2 times 5 equals -10. So there's our size. Now we could, the question, well, the answers are saying size. Now size is kind of considered scalar. The direction doesn't matter. Part D it matters for, whether it's upright or inverted. However, commonly a lot of these will just be saying, oh yeah, it's 10 centimeters tall. Okay? The fact that it's upside down doesn't matter to the perspective of the image. Like, if we use these sort of mirrors to create an image in, say, a television or a projector, it starts off upside down, and then the mirror will flip it to be the right way for us. So to us it looks 10 centimeters upright, but in perspective of whatever's creating the image, it's 10 centimeters upside down. And we can use lenses to do the same thing so that things flip around. But for this sort of thing, you can answer it as just positive 10 centimeters because they only care about the size, the magnitude of it. They don't care about the direction of it. Okay. So C, as we said before, it is real because projected. Now I know it's not asking us to explain how we know it's real. You can draw a ray diagram to figure that out actually, but it's always good to explain. Now if it's told it's projected onto a screen, or the image is being formed somewhere, it must be projected. Now finally, is it upright or inverted? Well, that -10 there now comes into play. So the negative means it's upside down, so that means it is inverted because m is negative. Alright. Okay, 25, 26, 27 are all 1 star. Let's go into 28. And 28 is asking for some ray diagrams. Okay, first off, we have a plane mirror, and we have an object that is 2 centimeters from it. Okay. So if we take it as a line, or let's take it as a line with a point on the end, that means it's going to be a line with a point on the end on the other side, and it will also be 2 centimeters away. There's not really any ray diagram to be drawn for this sort of question, because it's a plane mirror. There's nothing to be cast away. In fact, these three are all plane mirrors, so the objects are just going to reflect laterally across the mirror itself. It's not really something I would draw as a ray diagram of any with any sort of interest. Okay. Oh, I think it's actually asking for point O, but you get the point. Okay, so this next one is asking for ray yx. Now, definition, remember, of a ray is that, and this thing is 3 centimeters there, and 4 centimeters there, and 3.9 centimeters there. So this means this one will be the exact same on the other. It'll be 3 centimeters away, 4 centimeters away, and 3.9 centimeters. Again, it's not a ray diagram per se. I mean, we could draw straight lines from it because that's what the rays are doing. Or we could draw some sort of point here and do our, like for example, if I did a point here as my viewing point, well, this would be some angle away, and so the line would reflect, and then we would back trace it to get to the same point. But if you consider and do reflections of just simple objects in mirrors, it's not really particularly troublesome. Okay, C, horizontal mirror this time. Again, a little bit more complicated in its construction, but we still just have a simple shape. We know that that is 2, 3, that's 2, that's 1, and that is 3.5, which means whatever's on the other side will just be something like that, where it's 1, 2, 3.5, 2, 3. I really don't see the point in this sort of question. It's not actually. It's not a two-star question. This is fairly trivial and useless because they're plane mirrors, and plane mirror ray diagrams are literally just straight lines. So, not challenging at all in my opinion. Certainly not something that you'd ever see in an exam from me. Okay, 29. Figure 17.26, so what's below, shows the position of two mirrors 45 degrees to each other. A ball is placed at point X. Draw ray diagrams to find the image of the ball in the mirrors. Ooh, okay, so this one's a little more interesting. So we have our original position. So it is 1 centimetre and 2 centimetres. So let's start off with just the mirrors themselves. So it might look like it's just the same as before, because you go, oh, okay, well, it's just going to be 1 centimetre there to that one, and 2 centimetres, 2 centimetres to this one. And you'd be right. The first step is to just go, alright, well, there's that and that. But then this image is going to be visible in this, and this image will be visible in this. So the question then becomes, well, where does this image get created in here? And where does this image get created into here? Because these images are now objects for the other mirror. Okay, and that's why if you hold two mirrors, so like if you can get yourself a small mirror or something that's a little bit larger, put it behind your head off to the side while you look into another forward-facing mirror, and you'll see a whole infinite set of mirrors. There's some really great images or videos on YouTube where people create what are called infinity mirrors using tricks of one-way mirrors to create like a tunnel of mirrors down in a table. They look stupendous. I do recommend it. But this is the same sort of thing. So we're just going to draw one more set of images. We're not going to worry about creating a whole infinite set of mirrors. So the question is where are we observing it? Let's take the observer from here. So this image would leave here and hit here and bounce back. So we want to find, well, where is the halfway point between it? So if we were here, that would go to there and there, which means if we were to backtrace it, and that looks like to be about, pretty close to 3-ish centimetres, or 4 and 4, so it's going to have to be maybe 3.5 centimetres. So again, maybe another one there. And this one, well, if we're here, then this one is going to, well, it's straight down, so that means that it would create, hang on, so we want to look into that mirror, so it'll probably bounce to about there. Maybe not actually. Probably bounce maybe to about there, which means that this one would end up being roughly there-ish. Okay, and the thing is, then we go, oh, well, now this image is going to create an image in here, and this image is going to create an image in here, and they become the new objects again. And we would go on for infinity, but there's no need to keep doing that. It's just more of the same. So this recognizing these first 2 points, that would be a C out of a B. Recognizing these second 2 points, that would be the challenging part of this sort of question, and arguably could be considered an A standard, because you'd have to think about going into infinities. Now, you can do that with geometry as well, so using your ruler and making sure you get your distances and your scale correct. It's not too bad a question, actually. Okay, 30. So figure 17.27 indicates a light ray making an angle of 40 degrees with the mirror. The mirror is rotated so the ray now makes an angle of 10 degrees with the mirror. Through which angle does the reflected ray move? So let's draw this. Originally we are straight. The ray comes in at 40 degrees, leaves at 40 degrees. So that's going to be 40. That'll be 40, which means that that has to be 50, and that has to be 50. Alright, show the thing where Okay, and then afterwards, the mirror gets twisted so that this same ray is still there, but is now only at 10 degrees. And that means the incident, or the reflected ray, sorry, is now also 10 degrees, and that these two are now 80 degrees. Okay, so this ray is still at this starting point. This thing here has moved, well, we can figure that out. If it was originally 40, now 10 degrees, that has moved 30 degrees. Okay? But the question is, well, how far has this moved? Because we want to know if we let's call this ray, say, XY. And we'll call it here XY. Okay? And we'll call this ZX. So ZX has not changed. Okay, but the surface that it reflects, that XY reflects off, certainly has changed, and so hence XY has changed as well. So this axis has moved in 30 degrees, and so that's moved out 30 degrees, but now the change in angle here was originally, well, this was originally 100 degrees inside. Now it's 160 degrees inside. So if all other things are being equal, this ray has gone from bouncing 100 degrees to bouncing 160 degrees. So that means the change in XY must equal 60 degrees. Because if this has moved, and this isn't a physics type problem, this is a geometry type problem. So if this was originally covering tending an angle of 100 degrees, now it's tending an angle of 160 degrees, if we look at the differences we see, oh yeah, well this means that this ray has changed 60 degrees worth, because our original, though my drawing doesn't represent it well, our original line is in the same position. Okay. 37 is our next 2-star question, and I believe it is the last one. Alright, so we've got a table there of numbers. Now, I have gone and done this on Excel. Reload that up. So I'd recommend you do this in Excel as well. You can write down here image distance, so your DI, your image height, and you've got a whole bunch of different numbers there. And you are told that the actual candle is 4 centimeters, so your height of the object. So the first thing I want you to do is complete the table and work out, well, what is the magnification on this column. And each magnification is going to be different, okay? But you'll need to work that out. So I'm not going to copy the table, but your magnifications will be like 3, 1.5, 0.75, 0.6, 0.425, 0.325, and 0.25. Remember, height image divided by height object. So in order to complete that table, magnification equals height image over height object. Now the second bit is the useful bit. So this is an IP type question here. And I want you to graph magnification versus image distance. Okay. Now reading the language here, we've got mag, FM for magnification, versus image distance, DI. So this means the phrasing, that's going to be our x-axis, that will be our y-axis. So do that up. You can do that on Excel if you wish to. I would recommend it, because that way you can then do a trend line and bring up an equation. Alternatively, if you do it by hand, you can draw a trend line, because this is going to be a linear set of data. So you will see bang, 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 nice straight line. There's a little bit of a wiggle right at the very end, but because of rounding, I guess. from how they've generated their data. However, you will get a nice straight line. And if you find the gradient and you find the intercept, those will both be equal to 15. The y-intercept will be equal to 15. So always, those things are always of interest in these sort of situations. All right, so the next two questions, C and D, are asking us to interpret our graph. Our graph looks something like this, where we'll have roughly 0.5, 1, 1.5, 2, it goes up to 3 or so on mine, and this would be roughly 20, 30, 2 went up to, let's see, 40. I'm not going to copy over the graph, you guys can do that up yourself, but have a look at the graph there. We just need to read these off. So find the magnification when the image distance is 45. So if I have a look at this, I can put my thing in halfway between 50 and 45, read it over, and it looks to be around 2, which the answers give us is 2. D, from the image distance, find the image distance when the magnification is 0.5. So again, we're reading it again. 0.5 going up, it's a little bit above 20, 22, maybe 23, not 24, 25 is too high, so 24 would be a bit low. So I'd say about 23 centimeters. And looking at the answers, it gives us that it is 22.5 centimeters. Again, it's just reading off a graph. It shouldn't be too challenging. It's creating the graph that's the trickier part. Those two bits are pretty straightforward. Now, this bit is when it becomes an B standard or higher question. It wants you to find the focal length of the mirror using the graph. Now, it can be really tempting here to go, why don't I just use the, I've got the height, I've got the magnification, I've got distance, I can work out the distance of the image, and then from that I can work out what my focal point is. And we can. I mean, that's not hard. But you can read it off the graph as well. So if you think about it, the focal point, what happens, we're saying we've got a concave mirror. Okay, so we've seen other graphs of concave mirrors. I showed you one of those before, and if we go and put our object at the focal length, what magnification will we get? So if we make DO equal to F, what magnification will we get? Well, we know for a concave mirror, if we have our object at the focal point, no image is created. So if no image is created, that means the distance to the image is 0, or the magnification is 0, because the image doesn't exist. Okay, or that the image is being created inside the mirror itself. So if we think about that, well, where does m equal 0? M equals 0 at the y-intercept. So the y-intercept, according to the equation, is 15, and we can see, oh, well, that's what it is off the thing there. It may very well also be the gradient. This would be worthwhile to explore and try with another one. I might do that myself in my own time, possibly after this video. So I will make a note on the video itself. But you could quite easily do that. Now we can work it backwards as well. It is equal to 15 centimeters, but let's work it backwards. So we know that m equals 3, and di equals 60. But it's concave. Okay, that looks like it's fairly far. Let's imagine we didn't know this. Okay, perhaps f is really big. Okay, we don't know this, but this number is pretty big for most of the mirrors we've seen, so maybe it's actually going to be negative m. We don't know this yet, so let's see what happens. Let's assume that m is positive to begin with. So 3 equals negative 60 over do. So do equals negative 60 over 3 equals negative 20. Well, that doesn't make sense. We've got a concave mirror and we're putting the object behind it. That doesn't work at all. That must mean, therefore, let's write that, nonsense. Therefore, m equals -3 must be the correct one. All we've told is how much bigger it is. We haven't been told whether it's upside down or not. So let's try it with that. -3 equals -60 over dO. So dO will equal 20. And then we have 1 over f equals 1 over 20 plus 1 over 60. So that equals 1 over 20 plus 1 over 60 equals 1 over 15. And f equals 15 centimeters. Alright, so that's the end of the video. I will put into the description whether or not it was the gradient or the y-intercept that is giving us this value of 15, since both of them are 15, or at least pretty close to 15 with a bit of rounding. So check that out, and I will see you in the next video. Thanks guys, bye.